Record. Okay, let me hide this bar. Okay. Okay. So we have learned flux, the definition of flux, which means the electric field times the area. And we have defined two vectors for calculating the flux. The first one is, of course, E, the electric field, and the other one is the surface. Do you still remember the direction of the surface? First of all, if you have a surface like this, then what's the direction? It's perpendicular or normal direction. When we talk about a small piece of, let's say, surface, you can define actually two directions, because when you define perpendicular, it could be going up or going down for a small piece of surface. However, later on, we will learn in many cases, we need a closed surface. Once there's a closed surface, we always define the outward direction to be the positive direction of your surface rather than inside. So in this case, for a closed surface, by default, the direction of the surface will be only one. It's unique. Now, let's see more complicated cases. If the flux, if we want to calculate electric flux of a non-uniform electric field, what will happen? So consider a surface in a non-uniform electric field. Then what we can do is first, we need to know the direction of the strength or magnitude of the E. For example, if we take two testing point here and there, we'll see EI at this point is going this direction, and the strength is shown as the arrow. And the other E at point J, the direction and the magnitude are all different from EI. So of course, if you want to calculate the flux, of course, what you can do is you can, let's say, cut or separate the big surface into very small pieces, and then you can calculate the flux piece by piece. For example, for this piece, the flux can be calculated by EI times AI, which is a very small piece of surface area times EI. And of course, this by times, we mean the dot product. Do you still remember the definition of dot product of two vectors? It's a vector A. If vector A dot product vector B, it results in a scalar, and it equals to the magnitude of A times magnitude of B times cosine theta. What is theta? Theta is the angle of those formed by those two vectors, A and E. So in this case, let me switch into pen. In this case, theta is shown here. And in the other case, theta is greater. So then we can calculate the electric flux by a very small piece, and then another small piece, then another small piece. And then when you go through the entire surface piece by piece, you sum all of the electric flux together, you get the whole electric flux for the whole piece of surface. If you cut it into very small pieces, then what does it mean? It means you're not doing a sum. If it's infinity small pieces, then what you're doing is integral, right? So this is the integral. For calculating a non-uniform electric field, what we need to do is do a sum, or more accurately, an integral through the whole surface, which is E times dot product dA. Both E and dA are vectors. We have defined the direction of those vectors. And we also define the meaning of dot product. And then we do this, and then we do an integral for the whole surface. And then you can calculate the electric flux by any surface. Okay, now, let's say if there is a curved surface in the electric field, then the same thing. This time, not only the E is non-uniform, this time even the dA, or the surface, is non-uniform, because the direction of the surface is always changing. For example, surface at here, it has a direction of this, and surface at here, the direction has been changed. So now we're talking about a non-uniform surface, or arbitrary surface. When you have arbitrary surface which might be curved, then the same thing. We can do we can calculate the flux small p by small pieces. We first calculate a very small piece, and then another one. Then you sum all of the electric flux piece by piece, you get the whole electric field. And if the pieces are small enough, we can say this is integral. So the same thing. For calculating the electric flux, we can do surface integral for a curved surface. Now, what about, let's consider an electric field that is everywhere tangent or parallel to a curved surface. Then what will happen? If you know a surface, and then the electric field is always tangent to any point of the surface. For example, at this point, the direction of your surface is going, let's say, going up perpendicular to the surface, but the electric field is parallel to your surface direction, parallel to your surface, which means perpendicular to the direction of your surface. 90 degree here means theta equals to 90 degrees. Then if we want to calculate the very small piece at this moment, at this point, what's the electric flux at this very small piece of surface? It should be 0 when your surface and your electric field has a theta of 90 degrees, because cosine 90 degree means 0. So if your surface and your theta has 90 degree direction, then at this point, the flux is simply 0. Now, if the electric field is everywhere parallel to the curved surface, if we take a look at here, it's also parallel to the surface, and here it's parallel to the surface. But we define the direction of surface to be normal surface, then that means the vector E and vector A in this case is always perpendicular to each other. So theta is always 90 degrees. Then cosine theta is always 0. Then the flux should be 0. Simply means you can consider you have electric field which is curved in the field, and then you have a surface which exactly follows the curve of your electric field. If the electric field lines is in a curve and your surface is in the same curve, what happens is there's no any field lines go through the surface. It always go along the surface. If there's no electric field lines go through the surface, simply means the flux is 0. Does that make sense? Okay. Now, in another case, in this case, let's consider electric field is everywhere perpendicular to the surface and has the same magnitude E at every point. Then what's the then in this case, what's the theta between your surface vector and your E vector or electric field vector? Let's take this point as example. For a very small piece, if the surface, if the electric field has a perpendicular direction to the surface, then what's the direction or what's the angle between electric field and surface vector? Right. So first of all, let's take this point as example. So what's the direction of the surface vector? Perpendicular to the surface, which is in this direction. And also we know E is perpendicular to the surface too. Then they're both perpendicular to the surface. That means their angle is 0, right? So cosine theta is simply cosine 0. So what's the value of cosine 0? It's 1. So in this particular case, if electric field is everywhere perpendicular to the surface and E has the same magnitude, then the integral of E dot product dA becomes E times dA cosine theta, but the cosine theta is 1. Then it becomes E dA. E is a constant. Then you can take E out of the integral because that's a constant. Then the integral, the surface integral of the dA simply means the area of the surface A. Then it equals to E times A. Does that make sense? So far, do you have any questions? Okay, so we're getting closer and closer to the Gaussian, the Gauss law. So remember this conclusion: when your electric field is always perpendicular to the surface, and when the electric field is a constant in magnitude, of course the direction might be different, but the magnitude is a constant. What you can do for the electric flux is simply, finally, the integral becomes EA. E is the magnitude of electric field. A is the surface area. This is a very important conclusion. Okay, now Please take 3 minutes and think about this question, and let's see which one is right. Okay, have you made your decision? So who would like to select A or B or C or D? Okay, the answer is A, because as we said, you can consider the electric flux to be the number of field lines going through the surface. You can just count how many field lines go through the surfaces. For example, the field lines going through A is obviously more than that in B. For example, this field line goes through A, but it doesn't go through B. Also for this field line, and this field line. So intuitively, you can see there are more field lines going through A and then B. So the flux is, of course, stronger. If you do the calculation, of course, you can do an integral by E at any position. For example, here, this is E, this is dA. You can do E dot product dA and then do the integral. And after calculation, you still will be able to find the flux A is greater than B. So talking about this, actually, in daily life, do we have any similar cases like that? For example, if you have a fan, which is blowing the air, make the air flow. So let's think about it. Or if you try to blow some airs from your mouth to blow something, when you make the airflow by your mouth or by, let's say, a hair dryer or a fan, we can consider that to be making an air flux for a small piece of surface area, let's say a small piece of object. Do you think the air flux is greater to be closer or further from the source? Let's say your mouth or the fan or the hair dryer. Closer. Okay. Why? So one reason is, let's say, let's take a dryer as the example. Now you have a dryer. So when it blows, it's supposed to make the airflow straight forward. However, there are always some airs flow to the side, right? So finally, your airflow becomes like that. Does that make sense? Of course, no matter the fan or the dryer, it tries to make a barrel so that it can focus the flow to go in one direction, but you know it's always impossible to make absolute one direction airflow. It's always distracted by other factors. So in this case, of course, if you want to dry your hair fast, or if you want to get more airflow, let's say air flux, should you use the closer position or further position from the, of course, closer. The same thing. When you have a pointed charge throwing out the electric field lines, if you want to get more flux by a certain, let's say, area of a surface, you want to move it closer to the source. Okay. Now let's see this example. Which one get larger flux? Okay, let's see. So who's willing to select the option A or B or C or D? Okay, so first of all, which is A surface? Is it the white area or the light gray area? Light gray. Okay, then you understand that this question. So okay, let me think about. First, let's let's solve it by using intuitively counting. So I'll give you the answer first. Now, intuitively, why they're equal? The intuitive way is, as we said, the flux means how many of the field lines go through the surface. So let's compare A and B. Let's say if there is a field line go through A, this is the field line. If it goes through A, in this case, it must go through B. The same thing. So if there's a field line going through B, that field line must have gone through A, because A is perpendicular to the flux, and the bottom surface is parallel to the surface. So if we compare A and B, every field line go through A must also go through B. The same thing for every field line. This is intuitive way of solving this problem. Then you know the flux should be the same. Quantitatively, how to solve this problem? Let's define the surface A to be A. Then this is E. So what's the magnitude of flux on surface A? It's E A. You can also make it in vector format, E dot product A. And the direction of A and direction of E are the same. So theta equals to 0, then EA, it equals to EA. Now let's see B. For flux B, It's E dot product the surface of B. So let's say if this is theta, let's use another symbol. Eraser. Let's do not use theta because usually we use theta for the angle between E and A. Now let's define it to be beta or alpha, and any letter works. So let's say this is beta. So E dot product of B, let's say this is your surface B. What's the vector of your surface B? What's the direction of vector of surface B? The direction is going up. Then the angle between your E and B, let's say it's alpha. Then you will see alpha equals 90 degrees subtracted by B, right? So we can say E, so this is theta. Sorry, I used alpha, but let's change it to theta because usually we use theta to indicate the angle between your electric field and the vector of your surface. EB cosine theta. Cosine theta equals to what? Sine beta. As we said, if you do a geometry, you will see beta and theta. Beta plus theta should be 90 degrees. And then it becomes EB sine beta. B times sine beta. What's that? That's A. Right? So quantitatively, they're the same. So no matter you solve it quantitatively or intuitively, they're always equal to each other. Okay, now we have talked about how to calculate electric flux in electric field. Now let's talk about the closed surface case. The electric flux through a closed surface is defined by this. Phi E equals to integral, and then there's a circle. The circles on integral means it's a closed surface integral. So this is definition of closed surface integral. E dot product dA. The electric flux is still the summation of the fluxes through a vast number of tiny pieces that now cover a closed surface. When you divide the closed surface into small pieces, if the pieces are small enough or infinitely small, then that becomes the summation becomes integral. And then by default, as we said, we use the vector dA to be defined always pointing outward to the surface. Okay, then we will do some calculations of the flux through a closed surface. But before that, let's take 5 minutes break. During the break, do you receive the email of evaluation for the class? Okay, then please do an evaluation of the class. If if you can take 5 minutes to submit your evaluations, that will be very appreciated, because usually the problem for the course evaluation is there are not a sufficient student to submit the evaluations. When the evaluation is less than, I don't remember exact number, it's less than I think 30% or something, then the evaluation will not be valid. So in order to make the evaluation from students valid, there should be more than 30% of students submit the evaluations. So if you get the email, please use 5 minutes to submit a brief evaluation of the course. I'll appreciate your help. Thank you. What?
The an email from the
TA?
Yeah.
You want to know the
TA's
email? I don't know which. Do you know the name of your TA? Because for this class we have 3 separate workshop sections. Okay. Take your time.
Yeah, sorry.
No problem. Okay.
Yeah. Can you do it with a CRM?
Yeah, probably.
Yeah.
Let me try. Okay, so what's the CRM?
29235.
29235.
29235.
Okay, I got it. So your TA is users. Okay, I got it. Do you want to take a picture?
Yes, that would be good.
Okay, that's his email. So his name is Diego.
Diego Gates. Right.
Yes.
Thank
Okay,
you.
no problem. So do you have some questions to ask to the TA? So do you want to send an email to ask some questions?
Yeah,
to the
do
TA?
it today. Mhm.
Okay, maybe you can CC me so that if the TA responds slow or doesn't respond, I'll reply.
All right,
Yeah.
sounds good. Thank
Okay,
you.
no problem. Yes, guys. So if you need help from the TA, if you want to send him an email to make appointment to help you, you can always CC me. So sometimes if the TA responds too slow, if I am on the list, usually they will respond faster. Yeah. Just keep me CC'd. Oh, what happened?